Hello everyone, I welcome you all to this online classes. Today we are going to discuss about electric flux, which is represented with the symbol phi E for electric flux. So it is defined as the number of field lines crossing the surface, and that surface must be normal to the electric field. So the lines which are passing through the surface, and the surface is in a direction normal to the electric field. So it's purely represents the lines passing through the surface. So it's just a number. It may be a positive or it may be a negative, but just it is a number. So it is a scalar quantity. It is a scalar quantity. Before going to the electric flux concept, just let us consider area. So area is the physical quantity, is a vector or a scalar? Yes, area is a vector quantity. So if it is a vector, it must have both magnitude and direction. So let us consider a plane surface of area A units. Now for this plane surface, the direction is indicated by drawing a normal to this plane surface. So this is the normal drawn. So this normal indicates the direction of the vector, area vector. So N stands for normal drawn to the plane surface. So N cap means the unit vector which is indicating the direction of the area vector. So here A bar, the area vector can be written as A times, the magnitude is A times, and N cap indicates, so N cap is the a normal drawn to the plane surface, nothing but the unit vector along the normal. So area is a vector quantity, right? So this physical quantity is a vector quantity. Now before going to electric flux, this is the same analogy as that of the fluid efflux, which we already discussed in mechanical properties of fluids. So fluid efflux means the fluid which is outflowing. Let us consider a tube. So here this is a surface delta S, and so here fluid efflux, which is defined as how much quantity, volume of fluid which is flowing across the surface delta S in a unit time. Volume of the fluid which is flowing across the delta S units in a unit time is nothing but the volume flow rate or rate of flow of liquid through that surface delta S. So here we consider two cases. Let us say, so here we have a the direction of the fluid is in this direction along the right side. V bar indicates the direction of the fluid, and the surface is normal to the direction of the fluid because V bar and delta S both are perpendicular to each other. So if delta S is in such a way, then what is the direction of this area element delta S? Simply draw the normal to this area, right? So here n cap indicates the normal drawn to the surface element. So we can see that V, the direction of the fluid, and the delta S are perpendicular to each other, but the normal drawn to the area element and V bar, direction of fluid, they are parallel to each other. Both V bar and N bar are parallel to each other. So this is the first case. If V and delta S are perpendicular to each other, or V bar and N cap are parallel to each other. So in that case, what is the flux? That is the fluid which is flowing across the surface. The flux is given by the volume flow rate, volume of the fluid flowing through the area in a unit time. dV, V means volume by rate, the volume of the fluid flowing in a unit time. Simply it is V times delta S. This is the case when V bar and N cap both are parallel to each other. This is nothing but the equation of continuity. in place of area, A into V is always constant. In place of area, we consider a small area element delta S. So here simply the fluid flux is V into delta S. So now let us consider the second case, which is, let us say the area element delta S is not parallel to the direction of velocity. Here in this case, the area element is perpendicular to the velocity. So what we consider the volume of the fluid flowing through the surface. How the surface is? The surface is always perpendicular to the direction of velocity. But now here the surface delta S is not normal to the velocity vector. It is making some angle. So if you draw a normal to this area element n cap, so in between this direction of the fluid and the normal drawn to the area element, they both are making some angle. So here this area element delta S is not perpendicular to V bar, direction of fluid flow. So in that case, what we have to do is consider, yes, the area element is a vector. Now consider the projection of this area element. How we have to consider? The area element must be perpendicular to V. So projection of this area element, which is perpendicular to the direction, because if we have a vector, we can consider, so this is making an angle. Now let us consider this is an n cap, which indicates the direction of the area. So consider the projection of this area element in the direction of the velocity, so here projected area element in the direction which must be normal. So here I can resolve this area element into two components, cos component and sine component. So a component of area element must be perpendicular to the direction of velocity is considered, which is nothing but cos component delta S cos theta, right? So here now the flux will become, flux is nothing but volume flow rate. So here what is the area which is normal to V? The area element which is normal to V is not delta S, but it is delta S cos theta. Now the case. So V times of delta S cos theta. What is this delta S cos theta? It is the area element which is perpendicular to V. Right. So by using the dot product, we can write this as V bar dot n cap into delta S. So n cap indicates the direction of the area element and delta S indicates the magnitude of the area element. So this is the general expression. In case of V and delta S perpendicular to each other, or V and normal drawn to the area, if they are parallel to each other, simply the flux can be written as V into delta X. V into delta S. If V bar and n cap are not parallel, that is area element is not exactly perpendicular to the direction of the flow, then in that case the flux can be written as V bar dot n cap into delta S. So the same analogy which we used for mechanics of fluids, the same thing we are going to use for electric flux, right? The flux, which is a Latin word, means flow. So in case of electric flux, there is no flow of electric field. The electric field will not flow. Whereas in case of the fluids, there is a flow of the fluid from one place to another. But here the electric field will not move. So we don't have any flow of observable physical quantities. They are not flowing. The charge remains there, but their influence is spread around the space. So here electric flux we are going to define now. So here in the case of electric flux, even though we are saying flux means the flow, here the electric field is not physically moving. It remains there only. So from the earlier concept discussion, we said that the number of field lines crossing per unit area is directly proportional to the magnitude of the electric field strength. This we discussed in the class of electric field lines. So we said that the number of field lines crossing per unit area, that area must be normal to the electric field. The number of field lines crossing per unit area, that area must be normal to electric field is proportional to electric field lines. So this is the how we can represent the electric field lines and the magnitude of the electric field strength. That is, this is nothing but the density, number density. Number of field lines per unit area is proportional to the strength of the electric field or the magnitude of the electric field. Now, number of field lines. Number will become E times of A. Number will become number of field lines, nothing but the flux, electric flux. The number of field lines crossing through the surface is directly proportional to E times of the area. Right. So here, first case, in the same way what we discussed in the case of a fluid flux, the same way electric flux. Let us consider a uniform electric field. I consider a surface delta S. It's exactly perpendicular to electric field. So if we have electric fields like this, I consider a surface which is exactly normal. So if the surface is normal, the normal to the electric field. So what is the direction of this surface? Always draw normal to this electric field. So in this case, if E and delta S is normal to E, it means the normal drawn to the surface element, and E bar, they both are parallel, because delta S is normal and normal drawn to delta S must be parallel to the electric field. So in that case, delta S is normal to E, or we can say that E bar and N cap both are parallel to each other. So in that case, so what is number of field lines passing through the surface? The number of the flux is defined as the number of field lines crossing the surface, and that surface must be perpendicular. Yes, in this first case, the delta S is perpendicular to the electric field. So in that case, the flux lines is E times of delta A. So here the area element I consider is delta S. So the number of field lines passing through the delta S or the electric flux is proportional to the product of electric field and delta S from the definition of the electric field lines. Right. So here let us say if I increase this area element, if larger area element I consider, what happens? More number of lines will pass through that area element. It means that flux increases. Suppose if I increase this E, if I increase E means that stronger is the electric field, closer will be the electric field line. So if stronger is the electric field, more lines are passing through. Now if more is strong, so more number of lines are passing. So in that case also the flux increases. So as the area increases, the flux increases. As the electric field strength increases, closure will be the lines, means more number of lines are passing through the area element, so the flux again increases. Now in the second case, let us consider E bar, the electric field, and the normal drawn to the surface element. They are not parallel, but they are making some angle. That is, in the first case we consider this is the surface and this is the electric field. So the electric field and the surface element are perpendicular to each other. Now the normal drawn to the surface element and electric field are parallel. Let us say now we have tilted. So the area element was somewhat tilted. So in that case, the area element, so the direction n cap indicates the direction of the area element delta S. So here now we have to resolve this area element in such a way that the component of the area element which is perpendicular to electric field, so this component will become delta S cos theta. So what is this? The component of the area element which is perpendicular to the electric field. So the electric flux in this case will be E times, simply we have to write area if area and E are perpendicular, but area is not perpendicular, it's somewhat tilted. So the projection of the area element, which is normal to the electric field, we consider. So this is the area element normal to the electric field. So here, because of this cos term, the electric flux lines which are passing through this area will get reduced. In the earlier case, the maximum number of lines passing through this area element. So to see this, the generalized expression for the electric fluxes d phi e, the flux passing through the area element delta S can be written as E bar dot delta S bar. So it's a scalar product. That is why the flux is a scalar quantity. So here we have given three different orientations of the area element. So in the first case, what we said, the area element delta S and the electric field both are perpendicular to each other. It means the normal drawn to the area element n cap and the electric field, they both are parallel. If both are parallel, then theta will become 0. So if theta is 0, the flux will become maximum. In the second case, here E bar, the electric field, and the surface element, they both are parallel. So the electric field is if the electric field is like this, the surface is also like this. Means that there is no lines which are passing through the surface. In this case, the maximum lines are passing through the surface. But in this case, the electric field and the surface element both are parallel to each other. So the lines which are passing through this area element will become 0. Why? Because the normal drawn to the area element and the electric field, their angle is 90. So if theta is 90, the flux will become 0. So the other case, let us say if the area element, the normal drawn to the area element is making an angle 60 degrees, let us say. So in that case, the flux will become EA by 2. So out of these three cases, if the area is normal to the electric field, where you will get maximum number of field lines. So for that reason, we selected the area element must be perpendicular to the electric field, where we will get maximum field lines passing through the area element. Right. So here for a plane surface, open surface or a plane surface. So if you have a plane surface, what we said, the direction of the surface is nothing but simply draw a normal. So for a surface, I can draw a normal pointing away from the surface, or I can also draw a normal pointing towards the surface. So both are possible. So I can draw the normal away from the surface or towards the surface. So these are the two possibilities for the case of an open surface. So for our convenience, we select the normal to the plane surface, away from or towards the source, towards the surface. Right. So for the case of a closed surface, let us say a spherical sphere or a cylindrical conductor. So in that case, so here we imagine this surface as a combination of smaller elements. So I can divide this into a smaller area elements. Those are plane surfaces. So if we have a three-dimensional closed surface, so we divide this closed surface into smaller elements, each of plane surface. So each area element will become a plane surface. So for this, how to draw the normal for the case of a closed surface. So here the convention is that the normal for this closed surface is always outward. So it comes from in a surface which is pointing in the outward. So the normal is, it is outward from the surface. It's a convention followed. Whereas here we have a ambiguity. Can we consider the normal away from the surface or towards the surface? Whereas for the case of a closed surface, always the direction of the normal is outward. It's outward. So here, so by considering this way, we divided the element, its surface into smaller element, and we'll consider the flux through each area element, and by adding the flux through all the surfaces, plane surfaces, we'll get the total electric flux through this closed surface that we are going to see, right? So here we consider two different examples, right? Let us say a positive charge. We know that if for the case of positive charge, the electric field lines move away from the positive charge. Whereas for the case of a negative charge, the electric field lines are towards the negative charge. But always assume that for a closed surface, the normal is drawn, which is outward. So here in this case, the normal is outward. So in that case, E bar and N bar and cap are parallel to each other. So the flux will become positive. Whereas here, the electric flux is pointing inward and N cap is always outward. So here they are anti-parallel, that is they are making an angle 180. So in that case cos 180 is -1. So the flux will become minus, negative. So always outward flux is positive and inward flux is negative. So these are the convention. The flux which is flowing out of the surface, we have to consider it as positive. The flux which is entering the surface, we need to consider it as negative. So the electric flux through the surface delta S can be written in two different ways. So it can be written as the electric field multiplied by, what is this? The component of the area element, which must be normal to electric field. E times of delta S cos theta. Delta S cos theta is the area element normal to the electric field. Or we can write this as E cos theta times delta S, where E cos theta is the component of the electric field, which is along the normal. For this, delta S is a vector area element. So if we draw a normal, so this is a component of the electric field normal to the area element. So we can write in both the ways, right? So this is the flux through a small surface delta S. Now if I have a total flux through a surface S, so I can imagine this closed surface as a smaller elements of plane surfaces S1, S2, S3, so on. So calculating the flux through each surface, adding all the electric flux, we will get the total flux through the surface. Addition of the flux through the individual surfaces gives rise to the total electric flux. So the total electric flux is given as E bar dot delta S sigma over. So by adding all the electric flux through the surfaces gives rise to the total flux. Here we given approximately, the total flux is approximately equal to E bar dot delta S. The reason is here we are assuming that in this surface, in the smaller area elements delta S, the E is maintained as constant. E is constant in this area element, but actually E changes from point to point, but we assumed E is constant in that small elemental area delta S. So we can get an exact equation by considering this area elements as small as like a point. So as delta S tends towards 0, so we are approaching the area element as small as possible. In that small area element, the electric field is constant. So we can write, so by considering delta S as tends to 0, so you will get more area elements as the area element reduces. So you will get infinite number of area elements. So addition of the infinite area elements, so we can replace the sigma with the integration symbol. So the total electric flux through the surface is given by, if it is a closed surface, we can write it as an integral for a closed surface E bar dot ds bar. As delta s is very small, we can write delta s as ds. So the total flux is given by closed integral E bar dot ds bar. So this is about the flux, which gives rise to the flux number of lines which are crossing through the surface, and that surface must be perpendicular to the electric field.